In the social, economic, and economical background, it is required to use the material available on site. And that's why we must find the solutions to improve the characteristics of the soil. So the paper has some important keywords such as active clay, such as stream lime-treated clay, cement-treated clay, and freeze-thaw cycle. The structure of the paper is I'm really sorry, I'm really nervous. It's the first time I'm speaking English in front of so many people. So the paper is structured on 5 chapters: introduction, active clays in the context of freeze-thaw action, stabilizing active clays, testing methods, and monitoring the effects of hydraulic binder stabilization of active clays, and of course conclusions. I have written here the importance, the trends, and the motivation of this paper. So why is it important to stabilize active clays? Because we have more than 42% of the earth crust formed by clays. And considering the economical factors, chemical stabilization of clays is the most used due to the fact hydraulic binders are some of the most widespread in the world. Why am I considering the freeze-thaw action in this paper? It's because this action brings additional alternating stresses in the soil, so the foundation soil will be affected. The trends, as I said, the trends in founding on soft soils is the chemical stabilization because of the properties that the hydraulic binder brings when the chemical reactions occur. The motivation is, of course, as I said, the widespread of the clays in the Earth's crust and the composition of those expansive clays, because a lot of them contain a big percentage of smectites, or if you heard about Montmorillonite, and this brings a really expansive character to the foundation soil. I want to show you now some pictures, some degradations brought by the water content variations, because why do we say expansive clays? Why do we say expansive soil? Is on water content variation or moisture content variation, the soil modifies its volume. So when wetted, the volume increases, and when dried, the volume really decreases. So it brings to light structures. I forgot to say that it affects a lot the light structures, such as small houses or roads, pavements, appearing some really big cracks, such as this and this, or like this. As you can see here, it's a really nice example of an active clay during summer, when water is no longer in the soil, so the structure really changes. To conclude this chapter of degradations, I want to show you a sketch how active soil behaves under the influence of natural circuit of water. So when, as I saying, when wetted, because of precipitations, the soil increases its volume, creating an edge lift on the foundation. And when dried, it creates the uplift in this area, and like this, creating these cracks. The active clays in the context of freeze-thaw action. I said that volume changes are a result of water content variation, but of course of wetting drying cycles and freezing thawing cycles, because the heave caused by the freeze temperatures is also one of the important parts of this paper. Volume changes lead to structural changes. When water flows towards the frozen layer, the size of the pores increase, creating the heave from frost, and therefore the need for stabilization. I want you to present, of course, the mechanism of freeze-thaw action. So we have here the layers. We have the frozen layer and the water going through the frozen layer, because it's created a temperature gradient. So I want also now to extract a little volume of soil from there and to explain to you. During freezing, the temperatures advance slowly into the soil, creating like this the ice lances. When the ice lances are created, it's also created a cryogenic suction, and the water advances up into the soil through the ice lances. And to demonstrate you, I want you to see a short video. This is one with the creation of the ice lances. If you have a little patience, you will see at the microscope how the structure of the soil is changed during freezing. So now here the water freezes, and you know when freezes it increases its volume. So like this is created the heave from the freezing temperatures caused by freezing temperatures. And sorry. And now, if you want, if I may, I will show you the behavior of the soil when the ice lances melt. Of course, caused by increased temperatures. When melting, the ice lances create a film of water instead, and instead of the original structure of the soil, we will have just 2 parts and with a border between them. Like soil stabilization. The first step in order to have a chemical stabilized soil is to select the binder, and for that we have to consider a series of factors such as the type of soil. If we will have a soil with a plasticity index higher than 12%, we will choose lime, and if we have a soil with a plasticity index lower than 20%, we will choose the cement. Yeah, also we have to consider the construction type. If it's if it's not such a light structure, we will choose a smaller percentage of binder. The quality level to be achieved, the layer durability, the costs, and of course the environmental impact, because there are some binders that can affect the agriculture. This is the mechanism of cementation. We are stabilizing the soil in order to obtain new products, cementation products, and these cementation products created at the border of the particles are really influenced by the water content of the soil and of course the curing time of the material, because you know, such as in the case of concrete, this material needs time to achieve bigger strengths. So that's why you can see here that it's formed a really a stronger product than in the case of an early curing material. I was speaking about the improvement of stabilization, the improvement of the soil through stabilization. So we will, through stabilization, we will obtain lower plasticity index, a decreased plasticity index, a decreased dry density, so a higher grade level of compaction, and of course higher strengths of the soil. Lime stabilization is a cold treatment technique, so it uses less energy. That's why it's really suitable for the use in the whole world. All the cementation products are obtained through chemical reactions, and these chemical reactions modify the structure, achieving to new minerals. The reaction are the cationic exchange of, as you can, maybe you know, active clays, Montmorillonite respectively, has a really high cationic exchange, and it interacts really good with the hydraulic binders. The second reaction is flocculation, after that carbonatation, and of course pozzolanic reaction. The first three are short-term reactions which lead to improvement in consistency, but the most important is the fourth one, is the pozzolanic reaction, which is a long-term one and brings the durability characteristics of the new material. And here you have two examples, no, two pictures before and after the stabilization. The cement stabilization, of course, it's a chemical, also a chemical reaction. The Portland cement with the water creates another three products, and the most important one is, of course, the hydrated lime. We have, after we stabilize the soil, we have three steps to achieve in monitoring the new material. So we have the soil classification and determination of the necessary lime content, the fabrication, curing, and durability tests in laboratory. Of course, it will be nice also to apply all the tests on site, but for now the specifications are only for the laboratory, and the determination of strength and stiffness. The conclusions. The durability of earthworks and the road structures under freeze-thaw action focuses on construction works made in active clays, affected by changes of the structure and which will lead to deteriorations. A solution to this is treating active clays with hydraulic binders, and the latest approaches for the characterization methods are an increased number of combination between freeze-thaw cycles and the percentages of added binder. Of course, in future research, I consider that it should be taken into account the temperature values in the region and the duration of a freeze-thaw cycles, because in the lab we only simulate this cycle by freezing the sample for 24 hours and thawing it for 23. This is me not nervous like now. And this is a really sad house because of active clays. So do you have any questions?